Hi everyone, welcome back to Computational and Data-Driven Engineering. So this is the first lecture that I'm going to give in the course, which has followed the first two cohort classes. So generally the lectures will be released on a Thursday evening or Friday morning. And the content of the lectures will be that of the cohort the following week. So in the cohort there'll be opportunities to practice what is taught in the lectures on the Thursday and Friday. Suppose you're interested in creating a component which is very reliable and the values of that component or the strength of that component or some parameter of that component need to be within a very tight tolerance. How would you measure whether the tolerance of that component or the variability in the parameters that component exhibits is equal to a particular value? This is the sort of question that I want you guys to be able to answer this week. So, for example, if you had a 3D printed part, 3D printed parts can be made with lots of different infill patterns or infill densities. How would you analyze which infill pattern produces the strongest part? Or how would you analyze which infill pattern has the most repeatable strength? Sure, there'll be a spread in strengths, but how can we reduce the standard deviation of these strengths? This is an important question, and ultimately it will impact the performance of the machine, system, or device that you're creating. And this is the sort of question that you'll be able to answer after the next few lectures. For the coming week and for the rest of the course, I'm assuming some knowledge that you've gained from 10.022, Modeling Uncertainty, which you took, I think, last term. So these are all of the concepts that I hope you have understood and are able to apply this year as well. So for example, the concepts of confidence testing, testing some sort of hypothesis, understanding what a t-distribution is and how it relates to a normal distribution, understanding how to perform different types of t-tests and the type of statistical errors that can exist when you perform these tests. This is when you perform these hypothesis tests. This is all assumed knowledge. If you do not have this background or you've forgotten this background, I hope you can brush up by going back to your notes of Modeling Uncertainty from last term or looking through the earlier chapters of Montgomery's book. So this week there'll be one video lecture. This is the video lecture. There should be around 10 case problems for you to do in the cohort class. And also I'm going to introduce the 1D project and do a little bit of preparation for that with you. So the reading, the recommended reading for this week, or I shouldn't say recommended, I'd say it's the minimal reading for this week. A Montgomery's book, section 3.53 and 4.6. Montgomery section 5.51 covers F distribution and ratio of variances. And also single factor ANOVA section 5.8 of Montgomery's book. So last week we covered errors. We looked at the different types of errors and we paid particular interest in statistical errors. These are kind of random errors that follow some sort of pseudo-random distribution, like a normal distribution. And this ultimately affects the tolerances that we can expect our system to perform within. So this is why it's important to understand how these errors, the origin of potentially these errors and how they might build up. So if we're building a system, the system is obviously composed of components, and the tolerances and variability in these components all have their own pseudo-random distribution, and these pseudo-random distributions of these individual components add together to affect the performance of the final machine or system that you're trying to build. Ultimately, it'll affect the distribution of the performance, and that again impacts the tolerance that we can expect this system to perform within. So we spent quite a lot of time in the last couple of lectures looking at propagation of error and how we could predict the performance of the machine or system by analyzing the performance of the subcomponents. And we did this analytically using the propagation of error equation and numerically using a Monte Carlo technique. We also, especially when we're looking at the analytical technique, we're able to see which component was producing the majority of the error in the final system or the final machine. So that leads to an inevitable question. If we want to improve the performance of the overall system, clearly we need to increase the performance of some of the subcomponents that are contributing to the error or the spread in performance. So how can we test whether a change in the way that these subcomponents are manufactured actually reduce the variability in its performance? And that's the sort of question that you'll be able to answer after this week. Be able to compare whether a sample drawn from a population has a variance that is statistically different from a specific value, such as the population variance. You'll also be able to compare two samples in terms of their variances to see if they're statistically different. This is useful, for example, if you're making something with a particular process. You might produce or manufacture, say, electrical resistors, and you have two methods for manufacturing them, and you want to see whether the tolerances of the resistors are the same when you use the two different methods, or whether one method produces a much tighter tolerance in resistances than the other method. You'll also be able to understand how to use variances to subdivide a population into many smaller groups, each group with its own distribution, and then understand whether those individual groups are statistically different from one another or not. And this is a good way to understand how to group or subdivide a population. If there's a large difference in the distributions of these subgroups, then that's obviously a good way to subdivide the population. Then to do that, to do this subdivision, one way of doing it is using analysis of variance technique. So I'm going to teach you how to do that today, and I'll show you how to compute the analysis of variance F statistic by hand, and also next week in the classroom using Python. Okay, let's move on. It's often necessary to test whether a particular system is producing an output with a variance equal to a specific value or not. For example, let's just say we're manufacturing electrical resistors and we want to manufacture 100 ohm resistors within a tolerance of 10 ohms, so 10%. We could take a sample of the resistors we're manufacturing and calculate the variance in the resistance of these of this sample, and then do a statistical test to see whether it's equal or not to 10 ohms. For that, we would use a chi-squared test. Another example might be we're producing resistors using two different methods, and we want to compare whether the two methods are producing a similar distribution in tolerances of the resistance. So in that case, we would use something called an F statistic to check. We take samples from the two different manufacturing processes and calculate the variances and check whether those variances are statistically different or not using an F statistic. So this is the typical approach. There's another example which I've written down here, a similar kind of argument. Suppose that you have two samples that are 3D printed with different infill patterns, and you want to answer a question, does print pattern A have a larger variability in strength than print pattern B? So the way you would do this is fabricate samples, a range of samples, a number of samples with different infill patterns, measure their strengths, and then calculate the mean strength and standard deviation for the two infill patterns. And then we would write a hypothesis like this. S being the sample variance. The sample variance in strength of A is equal to the sample variance in strength of B. Sorry, S isn't the sample variance. S squared is the sample variance. S is the standard deviation. So standard deviation in strength of infill pattern A is equal to the standard deviation in strength of infill pattern B. This is the null hypothesis. And then the alternative hypothesis is that these two infill patterns have different strength distributions. So then we need a new test statistic to perform this test, because we can't do this with the standard Z test statistic that you're using for normal distribution tests on the means. Distribution and chi-squared test statistic is used for comparing two squared random values. One of the most common random values that we would probably want to check is the variance, or the standard deviation squared. Let's see if I can just write that down for you again. Pointer options, pen. So we know that the variance of a sample, S, or S squared for variance, is equal to the sum of the individual measurements that we have in our sample minus the mean of the sample squared divided by n minus 1, where n is the number of samples. So you can see here that this is a random variable and this is a constant. The mean will be a constant. Xi is a random variable from the population. Clearly, when we subtract these two things here, we're going to get another random variable, which we're then squaring. So we're going to have a squared random variable. So that's why the chi-squared distribution is particularly important, because it describes squared random variables, which is what this numerator is showing here. And we might want to use this squared random variable, or variance in this case, to test whether this sample variance is equal to a specific value. For example, the population variance. So this ratio of the sample variance to the population variance will give us a chi-squared test statistic. This test statistic we can look up in we can look up a critical value for a particular number of degrees of freedom, or n minus k, n minus 1, which is the degrees of freedom. We can look up the critical value for a particular significance level, for example, the 5% significance level, and then we can check to see whether these two variances are statistically different from one another or not. Clearly, if chi-squared is smaller than the critical value, then this will not be statistically, these two variances will not be statistically significantly different. If it's greater than the critical value, which we've looked up in this table, then we would have to conclude that there's sufficient evidence to say that these two variances, the sample variance and population variances, are probably different, and therefore something has changed in the population to produce this sample. So this is important when we might want to compare a manufacturing process to see whether the things we're manufacturing are still meeting a specification in terms of variability. In this case, we want to compare two variances from two different distributions to get an F statistic. An example of why we might want to do this is, let's see if I can turn my pointer on, just 1 second. An example of why we want to do this might be to see if a manufacturing process has changed. Maybe we're creating a product and we want to maybe tighten up the variance in the output of this, in the performance of this product. So we would draw a sample from the first manufacturing process. Then we modify the manufacturing process and create new samples and take a sample of those. And then we compare the variances of the two samples to see if they're different. When we do this type of analysis, the numerator should be the larger variance and the denominator should be the smaller variance. Okay, and then we will get an F statistic, and we should compare that F statistic against a critical value from the F tables, or we can also compute these critical values in Python. The way you do this is, because you have two variances here, there are 2 degrees of freedom that we would need to find the corresponding critical F value for. So we would look up, D1 is the degrees of freedom on the numerator, D2 is the degrees of freedom on the denominator. The degrees of freedom here, I should mention, because we're calculating a variance and because of Bessel's correction, the degrees of freedom is 1, the number of samples minus 1. So this is the number of samples used to calculate the variance of the numerator minus 1. And this is the number of samples used to calculate the variance of the denominator, minus 1. And you can see that the degrees of freedom affect the shape of the F distribution. A few things to note: the F distribution, of course, is continuous and it's positive. It's positive because we're squaring this random variable, so it's impossible to have negative values here. Yeah, so I think that's pretty much it. The most important point here is that this F statistic is used for comparing two variances, and the numerator should be the larger variance and the denominator should be the smaller variance. So now I'm going to show you how to perform a hypothesis test to see if two sample variances are the same. So the null hypothesis will be that the variance of sample 1 is equal to the variance of sample 2. The other possibility is that sample variance 1 is not equal to sample variance 2. So the alternative hypothesis is this. Then we need to decide the rejection criteria, the kind of confidence level, if you like, that we want to be sure that these variances are different. So this alpha equals 0.05 is a 5% significance level, which means in essence that we'll be 95% confident if the variances are different, if the alternative hypothesis has to be accepted. Of course, you can change this to 99% confidence level, alpha equals 0.01 or some other value, but usually for most engineering studies we'll set alpha equal to 0.05. Then we calculate the F statistic. Just as I showed on the previous page, we take the smaller variance and divide by the larger variance to get the F statistic. And then we conclude by comparing the F statistic against the critical value whether they're different. If this F statistic is higher than the critical value at alpha equals 0.05, then we will conclude that there's sufficient evidence to suggest that these two variances are different. And if this is a manufacturing process, then we would conclude that something that we've done in the manufacturing process, some change that we've made, has affected the variance. So I hope that's clear. Let's go on to the next slide. But what happens if we happen to have more than 2 samples that we want to compare? In this case, it's difficult or impossible to define a ratio to find an F statistic using the method that I've just shown you. We need some other method to compare 3 or more samples. Before I show you how to do that, I first want to talk about grouping, because I think this is an interesting way to understand a process that we will use in the end to compare variances. The technique that we'll show you towards the end of this is called analysis of variance. So here's an example that I shamelessly took from Wikipedia. Suppose that we're at a dog show and we're recording the weights of every dog that comes to this dog show, and then we make a histogram like this of the dogs that we've measured the weight of. Of course, there are small dogs and large dogs, and there are a range of different weights that have been recorded, so we get this weird distribution. What could be the reason for this weird distribution? Why does it look like this and not like a bell curve? This is a sort of question that we can use grouping and a technique called ANOVA and the F statistic, which we just learned, to help test our hypotheses of possible reasons for this odd-looking distribution. So the first way that we might explain this distribution, our first guess or our first hypothesis, is that the weight of the dog is somehow correlated to the age of the dog and also the dog's hair length, right? So this is our first hypothesis of a way of grouping these different dogs. We'll take maybe we think that all the dogs that have got short hair and are young happen to be very small, have a very low weight, whereas older dogs with longer hair probably are heavier. So maybe this is our first hypothesis. The second hypothesis might be that it depends on the purpose of the dog. For example, a pet dog, here's my pet dog Kiki, versus a working dog, like this guy's police dog, it's a big working dog, maybe we'll be able to explain its weight. Or maybe the build of the dog, whether it's an athletic dog or whether it's a skinny dog. So here's a very athletic looking dog. So maybe this is will explain the weight of the dogs, the distribution of weights. The third reason, which we might hypothesize could explain this weird distribution, are the breeds. Very small breeds, like my dog Kiki, will have a very low weight, and bigger dogs will have a larger weight. And maybe we can separate this distribution or break down this distribution into lots of smaller distributions that are related to the type of breed of the dog that we're looking at. So let's look at the first distribution. So this is the same curve which I showed you on the first page, and then we look at the short-haired versus long-haired and puppy dogs versus senior dogs, or the age of the dog. And then we check, we break down, so we look at, first of all, maybe all of the short-haired dogs and plot their weights, and we see a broad distribution. And then the same with long-haired dogs that are puppies as well, and we'll also see a very broad distribution. And senior dogs, it's very similar. The senior dogs with short hair are plotted here, and it's a very broad distribution. And the long-haired dogs also has a broad distribution. The circle here represents the mean weight of these dogs. You can see that all of these distributions have approximately the same mean. This error bar here represents the variance. You can also see that the variants of these populations are also very broad and very similar. Unfortunately, all of these means are very close together and fall within this broad variance. So these different groups have a very similar broad, very high in what we call in-group variation, very big in-group variation, and the between group variation, which is this group compared to this group compared to this group compared to this group, all of the means are very similar. So I can't easily identify that this this way of grouping the dogs will produce lots of mini distributions that are well separated that can make up this overall broader distribution. However, let's look at the purpose and build of the dog. So the build of the dog can either be light and or heavy, skinny or muscular, and the purpose of the dog could be a pet versus a worker. So now, if we look at the light dogs that are pets, we see a relatively broad distribution, slightly less broad than before, and the mean of this distribution is just here. So these skinny dogs, which are pets, are more likely going to make the bottom half, the bottom tail of this overall population. Okay, then we have the muscular dogs that are also pets. So this is this X2, this is this second distribution. Again, we have a relatively broad distribution, and but the mean now is separated. The mean value of this one is different to the mean value of the pets that are skinny. So we have some separation. However, because the variation is also quite broad, it's unlikely that this is a statistically different strategy for grouping the data. Then we do the same for the working dogs, so the skinnier working dogs versus the heavier working dogs. What we can say is that there is a definite separation between the heaviest working dogs and the smallest or lightest pet dogs. The variances do not overlap, and the means are well separated. So this is a reasonable way of sorting out these dogs and explaining this broad distribution. A better way, however, would be to group them by breed. So at the bottom here, we have a very small breed, maybe like a Chihuahua or something. And then we have a slightly bigger breed, maybe like the breed of my dog, maybe a Maltese. And then something slightly bigger, a sheepdog maybe. And then maybe a Rottweiler or something at the heavier end of the scale. And within the breed, the distribution of weights is quite small. So we have a very small in-group variation. However, between the breeds, there's generally a large between-group variation. So the distance from here to this mean here is large compared to the variance. So this would be a very good way of categorizing and grouping these dogs. The key point is that the variance within the group is very small, and the distance between the means is quite large in comparison to this variance. So this allows us to visually see that this grouping, this strategy of grouping the dogs by breed, produces a distribution, lots of small distributions that can explain this overall weird population distribution. However, what we would really like to do, this is very qualitative, what I've told you so far. We'd really like to test statistically whether this method of grouping the dogs is statistically significant, and how confident can we be about our grouping strategy. And based on this confidence, if we have a bunch of different grouping strategies, can we say which grouping strategy is more likely? Compare the in-group variation to the between-group variation. What I mean is, if we look at all of the different breeds and look at the distribution of weights, we have a small in-group variation. these weights are these weights are not very well separated. These weights within the breed are very close together, so the variation is very small. But the mean of all of these breeds, the mean weight of all of these breeds are well separated. This is quite far from this one, and this is quite far from this one, and so on. So these means are well separated. If we take all of these means and create a variance of the mean weight of the breeds, then we'll have a large variance of these mean weights, because all of these means are well separated. They've spread over a large range, these means. So we'll have a large between group variation, and the in-group variation is very small. You can see the error bar or the variance bars in this plot are very small compared to how far apart these means are separated in the between group variance. So this is a good thing. So if we use the F statistic now, and then we put the between group variation on the numerator and the in-group variation on the denominator, we're going to have a very large F statistic, which is an indication that the groups are well separated. So another way to look at this is using box plots. I'll just explain how box plots work. So if you take a data set and then you plot the minimum value on a line with a marker, and you also plot the maximum value in the data set on the line with a marker, and then you also plot the data where the value of the data where 25% of the data is below, and also you plot, this is called the first quartile. You also plot the 75% mark, the data value where 75% of the data is below, and you also plot the arithmetic mean as a line. So this is a box plot. You can represent between group and in-group variations using these box plots. So for example, let's imagine we have within the group a large variation in the weights of the dogs, and if we're using the previous example, and the means of these different variations, which are represented by these lines, are very close together. When we calculate the variation of the means of these different groups, we're going to get a very small, what we call between group variation. It's going to be a very tight distribution of means. This is not a good thing, because it means that our grouping is not great, because each individual group looks very similar. They all have a similar weight. They all have a very similar large in-group variation. However, if our grouping is good, so this is more likely to be the example where we're looking at age, the age of a dog being correlated with weight, or the hair length of a dog somehow being correlated with weight. It's highly unlikely that we'll be able to separate the dog's weight based on their hair length. This is more like the example where we separate the dog's weight according to breed. So at the very heavy end of the scale, we might have the Rottweilers, and there'll be a small in-breed variation in weights, and the mean will be very high, and that'll be very well separated from the next breed, which will also have a small in-group variation and a mean. So now you can see that the between group variation, which is the variation of these mean values, so we take all of these means for the different breeds and calculate the variance, we're going to have a very large variance in the weights of these different breeds. But the in-group variation, which is this blue box here, the in-group variation is very small. So in this case, if we calculate the F statistic, we have a large between group variance and a small in-group variation. So the F statistic is going to be large. This means that we have to reject the null hypothesis and conclude that these different groups of dogs are different, their weights are different. So this would be a good way of separating the dog weights, of separating the distribution of dogs by weight. In this case, we might have chose hair length as a hypothesis of a way to separate the weights of the dogs. In this case, the means are very close together, so we have a very small between group variation, and the in-group variation is large. So this small in-group variation, small between group variation divided by the large in-group variation is going to produce a small F statistic. So we would accept the whole null hypothesis and conclude that all of these groups are the same. There's no difference between these groups. In other words, hair length is not a good way to separate to categorize dog weights. In the case where we have more than two groups, we can't use the method that I showed you at the beginning for calculating the F statistic for two variances, because we have more than two groups, we have more than two data sets. So in that case, we use something called the analysis of variance, or ANOVA. So the way we do it is, first of all, set up our hypotheses. Usually, we want to test whether the means for each group are equal or not. So usually in ANOVA, they use the word treatment rather than group. So we want to test whether the effect of treating the data sets in different ways produces an equal result or not. And that's the null hypothesis. So treatment 1 or group 1 is equal to treatment 2 is equal to treatment 3, and so on. And the alternate hypothesis that is at least one of the groups is different to the others, i.e. at least two or more groups are different, significantly different. And then we have to apply the mechanics to calculate how much variance there is within the group and how much variance there is between the groups. So to do that, we calculate the mean of each group, the mean of each treatment. Then we calculate the total mean of the whole data set. Then we also calculate, you remember, we have to calculate how broad all of the means of all of these groups are separated. So we have to calculate the variation of between the means of the groups. So this is called the sum of square treatments. Then we have to calculate the in-group variation, because remember, we want a large between-group variation and a small in-group variation. So that's just the mean. The variation, the sum of the kind of the average variation of each group. That's what the sum of square errors means. And then we calculate the mean sum of squares between the groups and the mean sum of squares and mean sum of square errors, because ultimately we want to calculate this ratio of between group variation to in-group variation, the sum of square treatments divided by the sum of square errors, the in-group variation. And then we can perform an F-test to test whether these groups are statistically different or not. So I'm now going to walk you through the method of calculating the between group and in-group variation. So this is part 6 on the list on the previous page. So the between group variation is calculated using this equation, which I've put a box around. So essentially, imagine that we have A different groups or A different levels. So we have a certain number of groups, and within each group we've got data or measurements. That we can define a group index to define which group we're looking at, which is I. Okay, and then within each group we will have n different measurements or n different observations. Right? Then we can apply this equation. So this y hat, I dot, means the total of observations, the sum of all of the observations in a particular group. So this is just summing up all of those observations, right? And then if I divide then by the number of observations in that group, I will get the mean of that group. That's all that means. This is just shorthand for meaning the mean of the group, or the mean of that treatment. This y dot dot hat is the grand mean of all the observations that we've made for all of the groups. So what I'm now doing is calculating the square of the means of each group and subtracting it from the grand mean of the whole data set. So this is going to give me a variation, or something like a variance. You know, the variance is the difference between an observation and the mean squared, right? And then divided by the number of samples. In this case, I'm not dividing by the number of groups because to get the variance, because we actually have to do a correction, a Bessel, something like a Bessel correction, because the number of degrees of freedom needs to be taken into account. So the number of degrees of freedom is the number of groups minus 1, right? So we don't underestimate what the variation is. We need to do this correction. So that will give us, if we then divide by the number of groups minus 1, then we get the mean sum of square treatments, which represents how much between the groups the means of each group are varying. Errors, or the in-group variation, is calculated using this equation. Essentially what we're doing is looking at the variance of each group. So we take each data point minus the mean of that particular group from each data point in the group and square it and sum it up. And then we do the same for the next group, and then for the next group. Remember, A is the number of groups. So we do this for all of the groups, and then we get a sum which represents all of the groups, the variation of all of the groups. Now, to get the kind of the variance, or the mean sum of squares for the in-group variation, which we call the mean sum of square errors, then we need to take this variation and divide by the number of samples, essentially. So, but we have to do this correction. So, of course, the number of samples is A times N, the number of groups times the number of data points in the group. But because each group, when calculating the variation, we need to consider the Bessel correction. The degrees of freedom in each group is N minus 1. So we do this correction and multiply the number of groups by N minus 1. And this will give us a mean sum, kind of something that represents the variance within the group. This denominator, this mean sum of square errors, remember, the in-group variation becomes the denominator of the F statistic. Usually the denominators of a statistic are something like a noise. So the bigger this number, the harder it will be to separate out the effect of the treatment, or separate the different groups. So the total variation of the whole data set is going to be equal to the variation of the treatments, or the groups, the between group variation, plus the in-group variation. If we add those two together, that will also give us a total variation of the whole data set. Another way, a much more tricky way, if you like, to calculate, not tricky, tedious way to calculate the variation of the whole data set is calculate the grand mean of all of the data that you collected for all of the groups, and then calculate the variation of for each data point in the whole data set. So I calculate the mean and then subtract it from each data point, square it, and add everything together, and then I'll get the total variation, or something like the variance, the total variation of the whole data set. So this can be calculated in two ways. Some of the questions that you might experience in the exam, some simple questions, might be using these two facts to find missing information. So once we've calculated the between group variation, or the sum of square treatments, or the between group variance, I should say, the sum of square treatments, and the in-group variance, or the mean sum of square errors, we can calculate the F statistic. On the numerator, we have to put the treatment, and the degrees of freedom that you will have here is the number of groups minus 1, right? Because this is the group variance. And then on the denominator, it's the mean sum of square errors. The number of the degrees of freedom is n minus 1, because this is the number of samples in each group, multiplied by the number of groups. That will give us the degrees of freedom for the sum of square errors. We can look these values up in the table and then again compare to a specific critical value for a particular significance level, like a 5% significance level or something. So once you've done that, if this F value is larger than the critical value, we'd have to conclude that there's no statistical evidence to suggest that the groups are the same. That would mean that one group is going to be statistically significantly different to the other in terms of whatever test parameter we're analyzing. If it's the weight of the dogs, it would mean that one of the at least one of the groups has a completely different mean weight to the other groups if the F statistic is large. And again, we get this from looking up in the tables, or we can even use the SciPy stats module in Python and compute it in this way. So alpha is a significance level, this is the degrees of freedom, and this will give us a value for the critical value that we can compare against this. So to summarize, analyzing errors and analyzing variances is super useful. I showed that the chi-squared could be used to test whether sample variance is equal to a specific value. I also showed that the F-test could be used to check whether two sample variances are the same or not. And this is particularly interesting to see if a change in a process produces the same output specification or the same output variance in the final thing that you're manufacturing. In the last few days, we looked at propagation of error, and we could break down the source of error in a process and find out where an error is coming from. And then I said that if you could reduce the variation in that particular component, which is producing this distribution of the final error, if you could reduce the variation in that, then that would be a good thing, because then you'd reduce the variation in the final output of your process. This process here, this F test, and even the chi-squared statistic could be used, the chi-squared test, sorry, could be used to set an upper limit on the variation in a subcomponent that would then allow you to get a particular variation in the final machine or system that you're analyzing with the propagation of error. So I think this test is useful and can be combined with propagation of error to make it even more useful. The analysis of variance allows you to compare whether 3 or more different treatments or groups are the same. This is also useful for grouping things, and it's also fundamentally useful for something that we're going to study next week, which is design of experiments and optimization of designs. So in the next few classes, However, we're going to practice applying ANOVA and practice applying the chi-squared statistic and the F-statistic. So I hope this lecture has been useful. If you did find it useful, like and subscribe. Okay, thank you. Bye.